Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 7, Differential Equations. Today we're doing topic 7.8, which is exponential models with differential equations. Today's lesson is a calculator lesson, so you may want to have a calculator for today's work. And a reminder for calculators in AP Calculus AB, you should always have them set in radian mode, and if you're rounding, round to 3 digits after the decimal place. Enjoy today's notes. All right, welcome to 7.8 Exponential Models with Differential Equations. We're going to jump in a little bit, reviewing some pre-calculus things, talking about exponential functions, maybe a little bit from pre-calc, maybe a little bit from Honors Algebra 2. Some things we should remember about like our basic exponential functions is when we have something of this form, y equals a times b to the t, frequently especially in word problems, our a value is going to be the initial value. So it is the initial value for that exponential function. A lot of times we're talking about like population, we're talking about growth, maybe talking about decay. Half-life is a frequent thing that comes up. Talking about like growth weights that have lots of different things come up in these types of problems. The b value, though, is what's referred to as either the growth or decay factor. So our a value is our initial value, our b is our growth or our decay factor. It's the multiplier in that exponential function. It's the thing that gets multiplied repeatedly. And some review from our last couple classes. We can tell in exponential functions whether it's going to grow or decay by that b value. If b is positive, or not even just positive, if b is bigger than 1, we know that it's going to be an exponential growth. It's going to be growing over time. And if b is less than 1 but positive, we're going to have an exponential decay, which means that graph over time is going to be going downwards. Generally, I think maybe we could sketch those here on the side. But if we're talking about an exponential growth, this is your classic sort of function where, it's maybe going along the x-axis and then going upwards like this. Standard exponential has a horizontal asymptote. And then if we're talking about our decay, it's like the same idea as this, except sort of reversed, where it's starting up higher and then it's going down through that point, and it has this horizontal asymptote that's here for this. Both of these are exponential functions, and then generally exponential functions are really useful in sciences. Like virus growth is exponential frequently, so very relevant over these last couple of years that we've had. But let's take a look at this y is equal to a times b to the t. I want to take a look and we want to see if we can find some things that we can find that are true of these types of equations. So what I'm going to do is I'm going to take the derivative of each side of this equation with respect to time. So the left and the right side, we're going to do a little bit of an implicit differentiation here. So if we take the derivative of the left side of y with respect to time, we're going to end up with dy over dt. And that's going to be equal to the derivative of the right side here with respect to our time. The a is a constant, so it's going to stay there. And of our rules from back in Chapter 2 and Chapter 3, this is like an a to the x function, which you might remember has the rule that it's the natural log of whatever the base is. So the base here is b times that b of t function. So altogether, this is going to be a times the natural log of b times b of t. Now here, what we might notice is sort of interesting is that when we take this derivative, we end up with an a and a b of t here on the right side of this equation, which you'll notice is exactly the same thing as what we started out with before we started this problem. So this is the exact same thing as y, this a and this b together that are being multiplied. We just have this extra natural log of b. So what I'm going to do is I'm going to write this as dy over dt is equal to y times the natural log of b. And again, that y is coming from the a times the b of t, which we said back in our original problem is what y is equal to. Next, what we can do is we can say, well, we notice that if we take the derivative of this exponential function, that we're going to end up with the same function that we started out with, the y, right, the original equation, times some constant, right? Depends on what the base is in this case. But generally for this type of problem, they're going to always come of this form where we're going to say that dy over dt is some constant, which I'm going to just call k, times the original equation y for this. And so this is actually a super important thing to recognize, that when we have exponential functions that we start off with like this, that their derivatives are going to always be of this form. Dy over dt is equal to some constant k, which I'll just again mention that that's a constant, times the y function. Every single exponential growth and decay is of this form. And I'll just mention in general, we can tell looking at the derivative whether it's growth or decay based on the sign of our k value. So if it's positive, then our exponential function is growing. If that k value is negative, then that exponential function is decaying. And so that's a useful thing for us to notice if we're thinking about what the original y equation is. Great. The rate of change of a quantity is proportional to the size of the quantity. So the rate of change of a quantity, how quickly something changes, is proportional to the size of that quantity. So the bigger that exponential function is, the faster it's going to grow. The smaller it is, the smaller it's going to grow. This represents what's called an exponential model. So some of the problems that we have in this section and that we see on, the AP exam for free response and multiple choice are ones where we want to figure out context. So for this next part, we're going to say set up a differential equation for each scenario. Number 1, the weight of an animal is increasing at a rate proportional to its weight. Because we know that it's increasing at a rate that's proportional to its weight, we can say, since it depends on the weight, that it's going to be one of these exponential growth problems. And we would expect the derivative to be of this form of dy over dt is equal to some k times ry. Now, we'll use the variables that are in this problem. Because they're talking about weight, we're going to say that the change in weight, so dw, with respect to time, so dw over dt, that's the rate of change of the weight with respect to time, is equal to some constant, which we don't know, times the weight, right? It's proportional to its weight, so k times w in this problem. Now, we don't have enough information here to go any further than this, but I do know, just based on what they told me, that this would model this situation because it's the rate of change of the weight with respect to time, and it's proportional to the weight, so some k value times the weight. Nice. Number 2, a bacteria population is shrinking at a rate proportional to its population size. So the bacteria population, it's changing, right? So that we're going to say dB over dt, the change in bacteria with respect to time, it's shrinking at a rate proportional to its population size. So because it's proportional, we're going to have this k times the population size, which I'll just say is our b in this case, right? The number of bacteria for it. Now, because they said here in this case that it's shrinking, I am going to assume here that the k value should be negative. So k should be negative because it is getting smaller as time is going on. I'm assuming that when I eventually solve for it, I expect a negative number because it is shrinking in this case. If it was growing, then our k would be positive. Number 3, solve dy over dt equals ky using separation of variables. So this is separate from these 2 previous problems, but how would we do that? We've got t's, we've got y's, we've got a k. I'm going to get all the y terms on one side. So that means I need to divide by y on each side. If I do that, that's going to be 1 over y dy. And I'm going to multiply dt to the right side of my equation. So that's going to give me k times dt. So in this case, if I want to get that, if I want to figure out what y is, just like we've been doing with other separation of variables, we need to integrate each side of this equation. We need to find the antiderivative of each side of this equation. If we do that, 1 over y, the antiderivative of that is the natural log of the absolute value of y. And here we're taking the antiderivative with respect to t. There's no t here, there's just a constant. So when we take that antiderivative, it's going to become kt. So k times our t, it's going to increase that exponent by 1. So now there's a t when there wasn't one before. And then we have a plus c here on the end. After that, we want to get the y out of this natural log. And so what we can do is we can take e to both the left side and the right side of this equation. If we do that, we're going to have e raising up to the left side, which is e raised to the natural log of the absolute value of y, is equal to e raised to the kt plus c on the right side. Our e and our natural log, because they're inverses, are going to cancel out. And so that's going to give us the absolute value of y is equal to e raised to the kt plus c. And then two things are going to happen here for this last step. We're going to bring the c down out of this exponential function, and we're going to bring it as a coefficient. And then we would technically need a plus or minus here to get rid of this absolute value, but because there's going to be a constant in the front, that constant is going to essentially absorb that plus or minus. It could be positive or negative based on the scenario. So our final answer for this is y is equal to e times c, y is equal to c times e to the kt power. And this is super useful actually, because pretty much anything that we have of this form where the derivative of y with respect to t is equal to k times y is going to end up giving us this form. And again, for those of you taking AP Physics or getting ready for AP Physics, this is actually an incredibly useful thing in that subject area that gets used quite a bit. There's a whole section at the end of the year where you're going to need to be able to do this process and move forward from there. So what I'll just highlight is that this is pretty important, what we've got right here on the side. I'm just going to highlight important for today's notes. The solution to dy over dt, right, what we had over here, is equal to ky, is y is equal to c times e to the kt, where c represents the initial value of the model. So this is a nice thing to just sort of know. Yes, you could evaluate it each time, but it's one of those things that it comes up so often that this form is useful to memorize. Just again, seeing that if you start with dy over dt is equal to ky, that the solution, the general solution, is going to be c times e to the kt. Cool. Let's talk about this. So problem number 3, what have we got? We've got dy over dt is equal to 6y, and y is equal to 5 when t is equal to 0. So what I notice here is that this dy over dt is equal to 6y is of this form, right? We just have a k, which is our 6 in this case. So again, I could do separation of variables here, or if I recognize that it's of this form, I can just sort of jump to this solution format, which is going to be that y is equal to c times e to the kt. Now, what is our c? We don't know yet. We need to use sort of our initial conditions that they gave us, that we know that y is equal to 5 and t is equal to 0. And that's going to help me find out my c and then hopefully my k for this particular problem. So if we substitute in, well, our y is 5. That's equal to c times e to the k times our t, which is 0. So if we're evaluating for this, we get that 5 is equal to c times e to the 0. Anything to the 0th power is 1. So c times 1 is going to be just our c on the right side. And so we know here that c has to be 5 for this to work. And then our k is actually going to just come from whatever this coefficient is. It's going to come from that 6 in this problem. So my final sort of equation for this is going to end up being y is equal to our c, which is 5, times e to the 6t. Again, the c we found by plugging in for the initial condition, and then our k came from the coefficient of this differential equation here for problem number 3. Nice, that's a little bit of a shortcut. Again, the idea here simply being, if you recognize that that's a exponential model, you can jump right to that solution format without needing to separate the variables and take the antiderivative of each side. Let's try number 4, slightly different, but same format. dy over dx is equal to negative 3y. Hey, that's of this form. Nice! When y is equal to 4, x is going to be equal to 0. So because we recognize that this is an exponential model, we're going to jump right to that solution format, and we're going to say, all right, our answer is going to be of this form, y is equal to c times e to the kt power. And I want to find out what my c is. K is going to end up being that negative 3. That's useful to know. But what's our c going to be? So if we substitute these two values in for our x and our t or our y in this case, our t or an x in this case, we're going to get that 4 is equal to whatever c is times e to the negative 3 power times our t or our x, which is 0 here. So 4 is equal to whatever c is times e to the 0, which is, again, 1. So c is going to be 4 for this problem. What's our final solution then going to be? We're going to have y is equal to our c, which is 4, times e to the k, which is that coefficient here, that's negative 3, to the x, or t, depending upon whatever the variable is. But since that's an x there, I'm going to leave that as an x in this problem. So that would be our final solution. Our particular solution for this that has a derivative of negative 3 times our y, and it goes through this point, x equals 0, y equals 4. All right, problem number 5. An animal weighs 3 pounds at birth and 4 pounds just 3 months later. The weight of the animal is increasing at a rate proportional to its weight. Set up a differential equation for this scenario. How much will the animal weigh when it's 5 months old? Key thing I'm noticing here is they're saying the weight of the animal is increasing at a rate proportional to its weight. That is an exponential model. So because they're telling us that, I am sort of getting unlocked that I get to jump to this shortcut and say that I know that my answer, my solution is going to be of this form, y is equal to c times e to the kt power. Now I want to notice, what did they give us here in this problem? We know that at birth, the animal weighs 3 pounds. So when time is 0, the animal weighs 3 pounds. And we know that 3 months later, this thing's going to be 4 pounds. So when t is 3 months, the animal's going to weigh 4 pounds. So this is months. And then we've got weight for our coordinates that we've got here for this. So what I'm going to do is I need to find out what my c and my k are if we're going to find a particular solution that models this scenario. And so first what I'm going to do is I'm going to plug in 0, 3, and we're going to see what we can find here for this. So if I plug in my 0, 3, we get 3 is equal to c times e to the k times our time, which is 0. Luckily for us, anything to the 0th power is 1. So 3 is equal to c times 1, which means that c is equal to 3. From there, we know, and we can say here that the equation that we know so far is y is equal to 3 times e to the kt power. Right? We know that c value is 3, but we still don't know what k is. So what I can do now that I've got one of the variables, is I can plug in the other coordinate that they gave me, 3, 4, and that will allow me then to solve for k, hopefully. So let's see what we get. If we plug in our y, we get 4 is equal to our c value, which is 3, times e to the k times our t value, which is 3 months. So if we're trying to get that e to the 3k by itself, we're going to divide by 3 on each side. So 4/3 is equal to e to the 3k power. But if we want to get that k, that variable, out of this e, I have to think about what would cancel out an exponential function. Like what we've been doing earlier, we said, hey, thinking back up here, e's and natural logs cancel each other out. So what I'm going to do to get rid of this e is I'm going to take the natural log of both sides of this equation. So the natural log of 4/3 is equal to the natural log of e to the 3k. Because these are inverses, the natural log and the e are going to cancel, which means that the natural log of 4/3 is going to equal 3k. And if we divide by 3, we get the k is equal to ln of 4/3 divided by 3. So what is our final equation for this? Now that we've got this, we can say that our equation is going to be y is equal to, so I'll just put a line here, y is equal to 3 e to the k, which we just said was the natural log of 4/3 over 3 times t. So all of this is in the exponent of that e function. And I'll super zoom in because that was very tiny, but y is equal to 3 times e to the natural log of 4/3 over 3 times t. So the same k that we had here is now here in this equation. The last step for this problem, though, is they asked us how much will the animal weigh when it's 5 months old. Now that I've got both c and k, all I really need to do is plug in our t value here to find that. This would for sure be something on a calculator section, right? We're not evaluating this by ourselves. So if you've got your calculator handy, if we plug in this equation, we would get that y is equal to 3 times e to the natural log of 4/3 over 3 times t is 5 for that. And so that's all up in that exponent. And we end up getting, when we plug into our calculator, something around 4.846 pounds for this. So because the growth of the weight of this animal was exponential, we can use 2 data points to write an exponential model, which we just did, and then use that to predict weights in the future. So predicting that at 5 months old, this thing would weigh 4.846 pounds. Nice. All right, let's move on to our last page, if you want to turn to the final page, and then we'll talk here about number 6 to wrap up for today. So in general, some things to notice. Of this form, like y equals c times e to the kt, you know that it's going to be growth if it has a positive exponent. So for example, here we see y equals 5 times e to the 2t. That's going to tell me it's growth because that's got that positive exponent, that positive coefficient of that t. We know that it's going to be decay if it's got a negative exponent. So here we've got a negative 3t, sort of over time it would end up getting smaller. And if we think back to the beginning of this lesson, one of the reasons why this ends up being decay is we know that a negative exponent for this particular problem would be like y is equal to 7 times 1 over e to the 3rd raised to the t power. Because it's got that negative exponent, it could move down to the denominator. And now this 1 over e cubed is less than 1, which if we think back to the beginning of our notes, hey, we know it's decay when that b value, that multiplier, is between 0 and 1. So that's what's happening in this case, right? This is now less than 1, so that's creating a decay for this problem. But it's sort of hidden by the fact that it's got this negative exponent here. So something just to notice if you're trying to tell, hey, growth or decay. Now, a super common AP extension that we have is this thing that's called doubling time or half-life. So frequently these are problems where after a certain amount of time, like a bacteria population grows after like 4 days. That's an exponential model. And then half-life is very much tied into like radiation and radioactive materials, where if you leave something out, part of it's going to disappear over time. And the way that we measure that is what's called half-life. How long does it take for half of it to decay away, to go away for that? So let's take a look at problem number 6 and see what we can do based on what we've learned so far in this lesson. A population y grows according to the equation dy over dt is equal to ky. Hey, that's familiar. This sort of tells me, because I'm seeing that dy over dt is equal to ky, that we're talking about an exponential model here, where k is a constant and t is measured in years. If the population doubles every 7 years, what's the value of k? Nice. So how do we handle this? Well, we know because it's of this form dy over dt is equal to ky, we remember that things of this form have a solution that looks like y equals c times e to the kt. So I'm going to jump to that. We know that the solution is going to be of this form, c times e to the kt power. And from there, we need to figure out what we know about this population. So it doubles every 7 years. So for example, what we could say is, let's imagine that when this started, after 0 years, the population was 1. There's like 1 person. If it's going to double after 7 years, we could say 7 years later, it's doubled. Instead of 1, hey, now it's 2. Okay, well, that's useful. If that's the case, then we can plug into this equation. We can think about, okay, well, how would we solve for c? How would we solve for k in this case? Let's plug in this first coordinate, similar to how we did this one over here. We're able to make that equation. And And if we do that, if we plug in 0, 1, we're going to end up with 1 is equal to c times e to the k times our t, which is 0. Again, anything to the 0th power is 1. So that tells me here that c has to be equal to 1. So now we know that this is y is equal to 1 times e to the kt power. Now we just need to find out what k is. And what we can do is we can plug in our 7, 2 into this equation to help us find out what k needs to be. So our y value is 2. That's equal to our c, which is 1, times e to the k times our t, which is 7 for this. So 2 equals 1 times e to the 7k, or just e to the 7k power. And if I want to find out what that k is, we've got to get it out of that e equation. So we're going to take the natural log of both sides. We say that ln of 2 is equal to the natural log of e to the 7k. But the natural log and the e are going to cancel. So that's going to give me just 7k on the right side. And then we can divide by 7. So k is equal to ln of 2 over 7. So what is our k value? In this case, they're asking us just to find that value of k. So if I want to find it, this is our exact answer, ln of 2 over 7. But if for some reason we want to round or maybe use it in an equation, we could plug into our calculator and we could see here that our k value looks like it ends up being around 0.099. Again, we round to 3 digits after the decimal place when we're doing AP Calculus AB. That's it for number 6, though, and for today's notes. As what we've got as usual, please go on to the practice, try some of these, see how it goes, check your answers, and please check in with your teacher if you have any questions. Have a great day, and take care.